So I was asking Matt which piece of equipment I was supposed to break this morning, because okay. So today's topic is pre-periodic points and heights, and some of it will be a combination of those two, and some of it I'll just be talking about one or the other. Just in general, I mean, if you work over the complex numbers and take a rational function, then there are going to be lots and lots of pre-periodic points, or even periodic points, because, I mean, a point of period dividing n is just the solution to this equation. If you multiply it all out, this equation has degree, well, if phi has degree d, then this equation, when you multiply it out, will generally have degree d to the n plus 1. So you'll get d to the n plus 1 points of period dividing n, at least, if you count them with multiplicities. In any case, you'll get lots of periodic points, and similarly, pre-periodic points, right? You'd have phi to the n of z equals phi to the m of z. But number theoretically, one wants to know what the arithmetic properties of these pre-periodic points are. And a first natural question would be, can there be infinitely many of them, say, that are rational or defined over some number field? And I believe the first person who studied this question was Northcott, who wrote a short paper in the Annals in, I think it was the early 1950s. And it says the following. Take a rational function with algebraic coefficients, and let's assume the degree of phi is at least 2. By the way, throughout this talk, I may forget to mention that the map has degree at least 2. I'm always going to assume that. And then we can look at the pre-periodic points of phi, say defined over q bar. I'll just write q bar here. What I really mean is in p1 of q bar. So the point of infinity is also included there. So this is just the set of all algebraic points such that beta is pre-periodic. And what he proved, and I'm going to sketch the proof for you, is that this is a set of bounded height. And that's a very strong statement. In particular, it means if you take a number field, then the set of pre-periodic points in that number field, so in P1 of k of that number field, is finite, because there are only finitely many numbers of bounded height in any particular number field. Okay. So the proof is a nice, relatively elementary application of height functions. I'm just going to do the proof for periodic points, okay? And for pre-periodic points, there's an extra 3 lines, which you can find in the written notes. So the starting point is the height inequality I mentioned, height estimate I mentioned last time. Good. Which says that if you take a point alpha and hit it with the map phi, the height, the logarithmic height, gets multiplied more or less by the degree of the map, up to an O of 1, where the O of 1 is independent of alpha. And I kind of indicated this, but if you don't want to keep in mind the slightly messy definition of height, you can think of the height of alpha as simply being, as I said, the number of bits it would take to store alpha in a computer if you were going to write it out in binary in some way. All right? So what we do is we apply this to alpha and to phi of alpha. In other words, I replace alpha by phi of alpha in this equality, so it's still true, and phi squared of alpha, and so on, say up to phi to the n minus 1 of alpha. And I'm only going to use one, I only really need one inequality on this. So what do I have? I have the height of phi of alpha is greater than or equal to d times the height of alpha minus some constant that depends on phi but not on alpha. And if I replace alpha by phi of alpha, I get the same thing, but for phi of alpha, yeah, okay. But now I kind of substitute the first one into the second one. So this becomes d squared, the height of alpha. The problem is, of course, the d multiplies the constant also, so I end up losing d plus 1 constants. Okay? And you just keep doing that. And at the end, you get the height of phi to the n alpha is greater than or equal to something in terms of phi to the n minus 1 alpha, and then you substitute from up above. And when you do all the back substitution, you get kind of the expected quantity that phi to the n more or less multiplies the height by d to the n, but you lose, you just do the substitutions, d to the n minus 1 plus d to the n minus 2, down to 1, c. All right? And I'm just going to estimate this little geometric sum by something even a little bit bigger, so d to the n over d minus 1, c. All right? Yeah. What, this one? Well, I mean, this equals sign is two inequalities because of the O of 1. It says that this side is greater than or equal to that side minus a constant, and this side is less than or equal to that side plus a constant. So I'm just using the lower bound. Okay. And you could write it out with O. You could write it out with O of 1s if you wanted. Yeah, okay. I just thought it was clearer doing it this way, but in fact, maybe it's more confusing. Okay. So we have this final inequality down here. And this is true for any point alpha. But now suppose that alpha is actually a periodic point. Okay? So there's some n such that phi to the n of alpha equals alpha. So if I use that n over here, what do I get? I get that the height of alpha is greater than or equal to d to the n, the height of alpha, minus d to the n over d minus 1 c. And if you just rearrange this a bit, see if I can do this in my head. So you get a d to the n minus 1. No. Yeah. Let's just do it. All right. So I get, move that over there. So I get d to the n over, there'll be a d to the n minus 1, and a d minus 1, and a c greater than the height of alpha. Okay, but the point is that this is bounded as n goes to infinity, independently of n, right? Because the d to the n over d to the n minus 1 is, the worst case is n equals 1. So this is bounded, independent of n. So that shows that the height of alpha is bounded. Okay, which is what Northcott's theorem says. I'll also point out that the proof completely falls apart if the degree of the map is 1, right? Because this, as it should. Okay, is there any questions about that? Is that clear enough? One immediate corollary of this which is really not at all obvious, is if you take a rational function of degree at least 2, and if you take a list, say beta 1, beta 2, beta 3, of pre-periodic points, okay, distinct pre-periodic points, then the field of definition of these points has to go to infinity as I goes to infinity. I mean, this is just kind of turning around. Well, it's a little bit weaker than Northcott's theorem, but Northcott's theorem says that the set of pre-periodic points has bounded height. So there are only finitely many of them of bounded height and bounded degree, therefore the degree has to go to infinity. So this just follows from standard period of heights. Let me just, for example, and of course, for most rational maps, you really can't explicitly write down at all what's happening. But there are just a few rational maps where it's relatively easy. So if we take v of z equals z squared, what are the pre-periodic points of phi? Well, there'll be solutions of z to the 2 to the n equals z to the 2 to the m. Okay, so if you think about it, you get 0 and you get infinity, and you get let's see, roots of unity, the set of all roots of unity, and that's exactly what you get. And of course, it's a standard fact that if you take a list of distinct roots of unity, the field of definition goes to infinity, right? Because the irreducibility of the cyclotomic polynomial would certainly imply that. Okay, so that's an elementary, one of the few elementary examples. In general, estimating, how fast this goes to infinity, that's a hard problem, because it's analogous in some ways to the irreducibility of the cyclotomic polynomials, except these are sort of dynamical cyclotomic polynomials, and their irreducibility is kind of hard to get your hands on. Okay, that's the wrong page. Let's go to the right page. All right, the height satisfies this very, very useful inequality, which I just used in proving Northcott's theorem, which says that when you apply phi, the height more or less gets multiplied by d, which is more or less what you'd expect because phi is raising things to dth powers. It would be really nice if we could get rid of that. Okay. But at the same time, we want whatever function we're defining that has this property to still have number theoretic information in it, right? I mean, I can define a function h that satisfies this really easily for you, the zero function, okay? But it doesn't contain any information. So there's a construction of Tate, which he originally did for abelian varieties, and Nerone did something, well, more or less simultaneously, gave another construction, which carries over to the dynamical setting. And it's a very, very nice result and very useful for many sorts of computations. And it's certainly in the abelian variety case, it comes up in all kinds of important conjectures and theorems. And hopefully, presumably, similarly, things will happen in dynamics. But even now, it's a useful thing. So here's what the theorem says. So you take a rational map, again, of degree at least 2. And let me, are these betas or alphas? Beta, all right. If you take any beta, in P1 of Q bar, so take a point. I mean, just using this inequality, even with this O of 1 here, a natural thing to do is, if you divide by d, to kind of normalize things, then the height of 1 over d I'm sorry, 1 over d times the height of phi of alpha is more or less like the height of alpha. And if you repeat that, so I think it's fairly natural to look at 1 over d of n times the height of phi to the n of alpha. Okay? If the O of 1 here didn't depend on the map phi, you'd get something very nice out. But it does depend on phi. So if you apply this inequality, well, this estimate, to phi to the n, the O of 1 will depend on phi to the n. So it'll depend on n, and it's not quite clear what's happening. But it's certainly natural to see what happens as n goes to infinity. And the theorem is that this limit exists. Okay? And the notation for it is h hat sub phi of, I'm going to do that. I'm using betas, not alpha. H hat phi of beta. So this is the definition. And this is called the canonical height of beta with respect to the map phi. And simply putting that down, I mean, that's fine, but one wants to know that it has some reasonable properties, right? Because, for example, this limit, maybe it exists and it's always 0. So first, the canonical height actually has arithmetic significance because it's equal to the ordinary height up to a bounded amount. And we know the ordinary height is a measure of the arithmetic complexity of beta. So that's good. And the second property is that this canonical height actually has a similar estimate to the one at the top of this page without the error term. So that's what makes it canonical, that there's no O of 1 error term. But A and B here, in fact, characterize. There's at most one function, h hat of phi, satisfying A and B. And further, well, a trivial observation is that the canonical height's non-negative since it's a limit of non-negative quantities, so that's obvious. But it characterizes the pre-periodic points, in fact. So the pre-periodic points are exactly the points whose canonical height is 0. Okay. And again, for those who've studied elliptic curves or abelian varieties, it's essentially the same construction as canonical heights on elliptic curves. And the same theorems, because pre-periodic points, remember, for maps, are analogs of torsion points on elliptic curves or abelian varieties. Okay. So, let me sketch the proof of this for you also, which is a clever but not real long, so can do the whole thing for you. Well, I mean, how do you show a limit of real numbers exists when you don't actually quite know what the limit is? Well, the standard method from real analysis, you show it's a Cauchy sequence and therefore it converges to some real number. Okay, so the goal is to show that the sequence d to the minus n, the height of phi to the n beta, is Cauchy. Okay. All right, so we take d to the minus n, the height of phi to the n beta, and subtract off d to the minus m, say, height of phi to the m beta. And we want to show that that difference goes to 0 if m and n, as m and n both go to infinity, right? So let's take the absolute value of that. And the trick here is to write this as a telescoping sum. So see if I can get the indices correct. Let's start at I equals m, and I guess we then want to go to n minus 1. And we'll take d to the minus I plus 1, the height of phi to the I plus 1 of beta, minus d to the minus I, the height of phi to the I of beta. Okay? So this is a telescoping sum. At the bottom, you'll end up with the d to the minus m term. At the top, you'll end up with the d to the minus n term. And all the ones in the middle, they just cancel out from the sum, right? So I should put absolute value signs around this to make it equal, because I took absolute values there. But I'm going to use the triangle inequality, and I can write it like that. Okay. So this is the sum I equal m to n minus 1. Let's see. Let me pull a d to the minus I plus 1 out. All right? So I get the height of phi to the I plus 1 of beta that I'm going to write as phi to the, I'm going to write as phi of phi to the I of beta. Okay. Minus, I have an extra d here because I pulled out too many d's, and I have the height of phi to the I of beta. Now, if you think about it, what this is, this quantity here, is the height of phi of something, we call it alpha, minus d times the height of alpha. And that quantity is bounded, right, from this. The difference between the height of phi of a point and d times the height of the point is bounded. So this quantity is less than or equal to the sum of d to the minus I plus 1 of some constant. And if you want to be careful about it, the constant depends on phi, but it does not depend on beta or alpha, or well, which I'm calling alpha. So it doesn't depend on I or beta. And now I just have a partial geometric series here. I guess I didn't say it, but obviously here I'm going to assume that n is greater than or equal to m, say. So that. So maybe let me just take the sum from I equals m all the way up to infinity. Then I can sum the geometric series. And I'll get a d to the, yeah, if you sum the geometric series and then rearrange it a little bit, you'll get this, okay? This is what happens if I let n go to infinity, I get something a little bit bigger. Oops, sorry, there's a minus sign there. Did you catch that? Yeah, d to the minus m. And so this goes to 0 as m goes to infinity. N, of course, is greater than or equal to m. And that shows that the sequence is Cauchy, because as n and m go to infinity, the difference goes to 0. Okay? So the sequence converges. Showing that a sequence converges by showing it's Cauchy is, I mean, sort of one of the fundamental tools one uses in real analysis. It's actually not a very pleasant process if you do number theory, because even if you take a sequence of rational numbers, or in this case maybe logs of rational numbers, the Cauchy convergence property gives you no clue about the arithmetic properties of what the thing's converging to. So an interesting question is, sort of what are the arithmetic properties of the values of this canonical height? And there's actually not very much known about that for those who like studying sort of Diophantine approximation type things or transcendence theory. Anyway, that finishes the proof that the sequence is Cauchy, so the limit exists. That's good. So part B said that the canonical height and the ordinary height were the same up to a bounded amount. So this was the proof of part A, I guess. Part B, well, to do that, I'm simply going to take this inequality that I proved over here, which is true for every m and every n. And rather than letting m go to infinity, I'm going to take m equals 0. Okay, so it's legitimate. So what I get is that d to the minus n, the height of phi to the n beta, minus, well, when m is 0, I just get the height of beta. And on the other side, well, when m equals 0, I just get this constant over d minus 1. So the constant. And now, because I've already proven the limit, this limit exists as n goes to infinity. If I just let n go to infinity, this thing I underlined here becomes the canonical height. So I get the canonical height of beta minus the height of beta is less than some constant that's independent of beta. And that's part B. It says the canonical height minus the ordinary height differ by something that's bounded independent of the point. Okay. Part C, maybe I'll put the statement of the theorem back up so you can see the statement. Well, the first part of part C was that the height is non-negative. And as I mentioned, that's trivial because these quantities are non-negative and you're taking a limit of non-negative numbers. So that's easy. One direction here is also completely trivial, right? If beta is preperiodic, that implies that the height of phi to the n beta is bounded, independent of n, because this set of points, as you increase n, just cycles through some finite set. So it only takes on finitely many values. So that certainly implies that d to the minus n, height of phi to the n beta goes to 0. Oops. As n goes to infinity. Right. So that part's easy. The other part's also easy in some sense. So let's suppose that the height of the canonical height is 0. Why does that imply that beta is preperiodic? Well, if I look at phi to the n of beta and look at its height, that's the canonical height of phi to the n of beta up to some bounded amount, where the bound, remember, is independent of beta and independent of n. That's the key. But the canonical height, oh, actually, I didn't prove part B, did I? This was A. All right. I've done A. I'm doing C. We'll come back and do B in a minute, but I'm actually about to use B. Oh, well. So the canonical height behaves canonically that applying phi just multiplies it by d. But I'm assuming that the height is 0, the canonical height is 0, so this term just goes away. So what we get is that the height of phi to the n of beta is bounded independent of n. So the orbit, the phi orbit of beta, which is just all of these points, is a set of bounded height. But it's also contained in, all the points in the orbit are contained in some number field. I mean, these are in P1 of k for some number field k. I mean, for k, you can take the field generated by the coefficients of phi and beta, right? Because once you have the coefficients of phi and beta, if you apply phi to a point there, you'll just get another point there. So the orbit is a set of bounded height defined over a number field. And just from a standard property of heights, that implies that the orbit is finite, which is exactly the definition of beta being preperiodic. Okay, so that's easy. So that was part C. Part B is actually completely trivial. The canonical height of phi of beta is the limit of d to the minus n times the height of phi to the n of phi of beta, which is the limit of d times d to the minus n plus 1 times the height of phi to the n plus 1 beta. But this thing is, the limit of this is just the canonical height of beta. I've just shifted the index 1. Okay. In other words, once you know that this limit defining the height of beta exists, part B is automatic. Okay. So any questions about any of that? Canonical heights, that all looks good? Okay. So we now know, for example, if I take a rational function, say defined over Q, and the degree of phi is d is at least 2, then the pre-periodic points defined over Q, that's a finite set. And in many cases, it's, well, pretty much in any case, if you're given a particular map phi, the proof actually gives you an upper bound for the heights of the points in here. And then you could check all of them in principle if the bound's not too big. And there are other methods for kind of pinning down what this set is for any particular phi that I give you. So z cubed plus 7z minus 1 over 3z plus 8. It's not that hard to actually figure out all the pre-periodic points they defined over Q. But if you start to ask sort of uniformity questions, I mean, how big can this be as you change the map phi, then you get into very interesting questions, which are primarily still conjectures. And again, they're analogs of what are in some case theorems, and in some case, well, they're theorems for elliptic curves and conjectures for abelian varieties. Okay. Which, oh, this one. If I move it, did it focus itself? No. There it goes. So I didn't break it, but I'm stressing it. Okay. So what would be a natural thing to think about this? I mean, how big can this be? Or even, well, how large can that be? How many periodic points can you get? Well, if you let phi have very large degree, you can create maps that have lots of periodic points, right? Because, for example, just to require, say, that phi squared of 0 is 0 and phi cubed of 1 is 1. Basically, these will just put relations on the coefficients of phi. And then you can just kind of solve for coefficients. And as long as you put fewer conditions on than there are free coefficients, you can kind of create maps that have periodic points. Just as if you want an abelian variety with a lot of rational torsion points, that's easy if you let the abelian variety have high enough dimension. I think that's right, yeah. Okay, so what you really want to do is kind of restrict the degree of phi, and then ask that question. So that leads to the uniform boundedness conjecture. Which Patrick Morton and I made a few years ago. I'm going to state it first just for rational maps in one variable over Q. And then I'll give you the general statement, okay? But even over Q, it's really still pretty much open, okay? So the conjecture here would be there exists a constant depending only on D, such that for all rational maps, say with rational coefficients, of degree D, the number of pre-periodic points that are rational is bounded by this constant. So independent of the map, other than depending on its degree, which you pretty much have to put in there. Okay. So next time I'm going to prove some theorems which will, well, at least for periodic points, the one I'm going to do, will show how to get an upper bound here that unfortunately it does depend on phi, but in a somewhat weak way. And Rob in his talks is actually going to give, I believe, even stronger bounds using p-adic methods. Oh, Rob's not going to do that. Okay, there exist much stronger bounds using fancier p-adic methods that you can find in papers of Rob's and Matt Baker's. But the really hard thing here is to get something that's independent, would be to get something independent of phi. Just on elliptic curves, it's not that hard to give reasonably strong bounds for rational torsion points that depends very weakly on the elliptic curve. But Mazur's theorem says that it doesn't depend on the elliptic curve at all. And that's much, much deeper. Okay, so there's a conjecture. And it's reasonable to think that maybe this is a hard conjecture in general. So as with most subjects, especially discrete dynamics, one always starts with the very simplest non-trivial case, which is quadratic polynomials. So how about just looking at quadratic polynomials? And if you study complex dynamics, you'll usually find a chapter or even two just devoted to the dynamics of quadratic polynomials. Oh, by the way, this is a general quadratic because, I mean, you could take ax squared plus bx plus c, but you can conjugate it, so the dynamics won't change to put it in this form. So it's really just a one-parameter family. And let's not make things complicated with pre-periodic points. Let's just look at periodic points, okay? So here's a theorem. First, it's very easy to get rational periodic points of period 1, 2, and 3. Okay? So there exist infinitely many rational numbers such that phi c, maybe I'll set some notation on the fly. The periodic points of phi c that are rational, and I'm going to create a new notation that I haven't actually used anywhere. But it's the analog for the notation in for elliptic curves. So these are points that are periodic and have exact period n, okay? Such that there are infinitely many rational periodic points. I'm sorry, no, such that that can't be true. That contradicts Northcote's theorem. That this is at least one for n equal 1, 2, and 3. I think maybe I've stated that in a confusing fashion. There are infinitely many rational c values so that this has a rational fixed point or a rational point of period 2 or a rational point of period 3. Okay? And that's a nice exercise, actually. For 3, the algebra is actually a little bit messy, but it's not so bad. And Patrick Morton proved that if you look at rational periodic points of period 4, there are none. Okay? So there are no rational C's for which a quadratic polynomial has a rational periodic point of exact period 4. Okay? And the proof reduces it to showing that a certain elliptic curve has no rational point, well, has only finitely many rational points, and they correspond to like c equals 0, c equals infinity, which doesn't count. Okay? Much trickier. Victor Flynn, Bjorn Poonen, and Ed Schaefer, and one name I'll write, 3 names, you just get abbreviations, proved the same thing for period 5. So there are no C values that have a rational periodic point at period 5. And to do this, they had to show that a certain curve of genus, they had to find all the rational points on a certain curve of genus 2, which at the time was actually quite a feat. Now it's, on genus 2 curves, that's become somewhat mechanized. So Sage or Mathematica or Maple will compute something like, we'll do the computation fairly quickly. All right. And just last year, Michael Stoll did the same thing for 6, well, conditionally. Okay. All he needed to do was he needed to assume that the Birch-Swinnerton-Dyer conjecture was true. Okay. Well, I mean, not the full conjecture. He ends up with a certain abelian variety of dimension 4. And he needs to know that the rank of the Jacobian, the rank of this abelian variety is 2, I think. 1 or 2. And it's just, the numbers are too big to actually do a descent on it directly. But assuming Birch-Swinnerton-Dyer, you can calculate the L series enough to check that the rank is what he needed. Okay? So then there's 7, 8. So there's a whole list of PhD theses here for grad students. So there's a 7 and an 8 and a 9. No, and conjecture, which Bjorn Poonen made, was that it's empty for all n at least 4, which seems like a fairly reasonable conjecture, though of course at the time he made the conjecture it was only known for 4 and 5. And it's now sort of known for 6 if you believe Birch-Swinnerton-Dyer. What Bjorn also did was, and you could similarly ask, you know, what kind of pre-periodic rational points can you get? So the periodic points give you a loop, and now you're asking also what kind of tails. And Bjorn, assuming that this conjecture is true, Bjorn figured out kind of all the possible tails also, which was a significant amount of work because you end up with a lot of curves you have to analyze. So like you can get points that have tail 1 and then period 2, I think, or period 3. Well, I think there's one. This is dangerous because Bjorn's in the audience and they'll tell me if it's wrong. I think you can get one that has period 3 and 2 things going on. Where is Bjorn? Can even get more than that. Rob knows the answer. Okay, but there's just a small number of pictures. Okay, and I mean another project that would be quite interesting. People wanted to do it, right? Is to replace Q by some quadratic number field and see what happens. See what kind of lists there are. See what kinds of pictures you can get. Okay. I'm sorry. Yeah, that's a good question. How big can this be? And the answer is that set can be infinite. So obviously you can't quite have this kind of thing. Rob actually already mentioned good reduction versus bad reduction. If the map has good reduction, then this set's very small, and you can analyze it entirely. But if there's bad reduction, which is kind of the situation where you get chaotic behavior, it can be an infinite set. But obviously countable because but it's certainly an interesting question to try to analyze this, but you won't have boundedness theorems of this sort. Any questions? Okay. So as I promised a couple minutes ago, let me give you the general form of the uniform boundedness conjecture. And of course, there's some question whether it's worth making conjectures this strong when one can't even prove the absolutely weakest non-trivial case, but what the hell. All right, so this is actually the one time during the talk I'm going to do something in dimension higher than 1. Though, of course, a lot of what I've said, it's interesting to study in higher dimensions. So let's take a a map, instead, not necessarily on P1, but on Pn. But I want to require this to be a morphism, so it's everywhere defined. Okay. And since we want to do number theory, I'll assume the map, is given by polynomials with algebraic coefficients. Let's let the degree of the map be d, at least 2, as usual. What else did I want to? Just want to get all the notation correct. All right, yeah. And let's fix an integer d. No, actually, I guess I want to do this the other way, the way I've been doing it. So let's take a number field of degree, I'll call the degree capital D. All right. Then I can ask for how many preperiodic points are there defined over this number field. Okay. And Northcott actually did this case also. He did Pn. The proof's identical because the height function has the same kind of property on Pn as it does on P1, that it multiplies the height by the degree of the map. It's essentially the same proof. So this set's finite. And one wants to know how big it is. And the conjecture would be that it's bounded by a constant that depends in as minimal a fashion as it can on the the various quantities. So it depends on the degree of the map, D. It depends on the dimension of the projective space, and it depends on the degree of the field. Okay. And just to give an idea of the strength of this conjecture, maybe I'll call this the uniform boundedness conjecture, DND. So if you could prove this for any one choice of little d, capital N, and capital D, that would be an amazing breakthrough. Right. The quadratic polynomial case, even if you could prove that, it's not even the full case. So that's degree 2 maps, but specifically degree 2 maps that are polynomials. Anyway, the conjecture for degree 4 maps on P1 for fields of degree 1, so just over Q, this implies, in a quite trivial fashion, Mazur's theorem that the number of rational torsion points on an elliptic curve is bounded by an absolute constant, independent of E. Okay. And one could turn it around and use Mazur's theorem to prove that, well, a uniform bound for the number of preperiodic points for a family of maps related to elliptic curves, but that's kind of cheating. Okay. So that's the sort of general conjecture. Okay, so what do I have? I have like 2 or 3 minutes, which is perfect. I want to mention one other conjecture, which is an analog of a very classical problem in number theory. Okay, so the conjecture due to Lamer. Although he asked it as a question, and in his paper, the way he phrased the question, it kind of makes it sound like this conjecture, is the opposite of the way it's now conjectured, but he still gets credit for the conjecture. It's a nice problem. If you just look at algebraic numbers, okay, then when do they have height 0? The height's always non-negative, but when does it have height 0? Well, in fact, the proof we gave, more or less, answers this question, because the ordinary height is the canonical height for the map z squared. Okay. But in any case, the height is 0 if and only if beta is a root of unity. And Lermer's question was, how small can you make the height if it's not a root of unity? Well, I mean, there's you can make it as small as you want in some sense, because, for example, if you take the nth root of something, like the nth root of 2, just from the linearity property, that's 1 over n times the height of 2. So the correct question has to relate how small the height is to the degree of the number field where the point sits, okay? And Larimer's conjecture is that there exists an absolute constant such that if beta is an algebraic number that's not a root of unity, then the height of that point is greater than or equal to this constant divided by the degree of the number field. Right? I mean, you can kind of exactly get that kind of estimate by taking these nth roots. And I mean, aside from the intrinsic interest, because it's really telling you something about the number theory of algebraic numbers, estimates like this are used in solving Diophantine equations. They also come up in lots of other contexts. Because Diophantine, it's related to Diophantine approximation, which in turn is related to whether certain power series converge. So it comes up in analysis also in various places. Okay, so that's Larimer's conjecture. And one can do a completely analogous thing over number fields. Oh, by the way, this is not known. The best that's known, let me call this degree D. Okay, so that's a conjecture. There's a theorem that the height of beta is greater than or equal to C over D times log D over log D cubed. Okay, this is due to Dobrovolsky, and that's the best. I'm sorry, the minus 3. Gotta get some of it. So it's pretty close. But, right. So this is a slightly worse estimate because this side's slightly smaller than that side. Yeah. So here's the dynamical analog of Larimer's conjecture. Take a rational map of at least 2 as usual. Take an algebraic point that's a wandering point for phi, so it's not a preperiodic point. So its canonical height is not 0. So you want to know how small it is, and the conjecture is that it can't be much smaller than some constant that depends on phi, but not on beta, positive constant, of course. Divided by, again, you have to put the degree of beta in, because you can do the same thing by taking inverse images of beta by phi, just like taking nth roots here. It would be wonderful to have a Dobrovolsky type of estimate for this. Okay, in general, you know, I mean, maybe try to prove that the height is bigger than a constant, at least that it's no worse than polynomial. You know, that there's some C prime here, also independent of beta, so that you have an estimate of that like this. This also is not known in general. It's known in the in Larimer's conjecture case. So it's known for the map Z, phi of x equals x squared, which would be this case. But nothing like this is known in general. And it would, again, it'd be interesting sort of dynamically, arithmetically, and also has potential applications to answering various questions about how points behave in orbits. Because remember, if you want to study the orbit of beta, how the height grows tells you how sort of arithmetically complicated beta's getting. And this is growing like d to the n times the height of beta. So if you know the height of beta is not too small, it tells you that the points in the orbit are, you know, getting bigger and bigger. Well, it gives you an estimate for them. Okay, thank you very much. Any questions? Comments? Yeah. An explicit no. People really haven't even done enough experiments to, I mean, for example, for rational maps of degree 2 over Q, I don't think there's, well, no, that's the one case. I take it back. Michelle did that in her thesis. Michelle Manus over here. So you can ask her for that. For degree 3 and higher, I don't think anyone